I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
Have you ever thought about light, not just as something that lets us see, but as a tool that could literally save the planet? As climate change accelerates, with rising temperatures, violent storms, and fragile ecosystems breaking down, humanity's need for bold, science-driven solutions has never been greater. While we often look to wind turbines, electric vehicles, or carbon capture for answers, a quieter revolution is taking place, one that doesn't just react to climate change, but helps us see it, measure it, and fight it using the most fundamental force in the universe: light. This is the world of photonics, the science of generating, controlling, and manipulating photons. Photonics once belonged mainly to optics and telecoms, lasers, fiber optics, and data transmission. But now, it's rapidly becoming one of our most powerful climate technologies. It's driving cleaner energy, smarter industry, and more precise environmental monitoring. And it all begins with one simple idea: that light interacts with matter in ways electrons can't. Unlike electrical systems, which push charged particles through metal wires and waste energy as heat, photonic systems use light itself to carry energy and information. That means faster speeds, less loss, and incredible precision. Imagine information and energy flowing at the speed of light, literally. Because of this, photonics gives us an unmatched ability to sense and control our world. Lasers can measure atmospheric gases across continents. Spectrometers can identify pollutants without ever touching them. And fiber optics can serve as intelligent nervous systems for entire cities, monitoring stress, vibration, and temperature beneath our feet. Nowhere is this power more transformative than in renewable energy. Solar technology is being rewritten through photonics, quite literally at the nanoscale. Engineers are designing solar cells that trap light instead of reflecting it away. They use nanogratings, resonators, and photonic crystals to capture every possible wavelength of sunlight, squeezing out every extra photon of energy. New perovskite silicon tandem cells use photonic textures that guide light deeper into ultra-thin layers, generating more power with less material. Quantum dot converters are even being developed to reshape sunlight itself, transforming low-energy or high-energy photons into the perfect range for maximum efficiency. In concentrated solar power, those massive mirror farms that reflect sunlight to a central tower, photonic composites are replacing old materials with high-temperature absorbers that can reach over 1,000 degrees Celsius. That's enough to power next-generation turbines or even produce green hydrogen directly from sunlight. And it's not just solar. Wind energy, too, is now guided by light. Modern wind farms use coherent Doppler LiDAR, laser beams that read air currents in 3D, helping turbines adjust in real time to maximize efficiency. Photonics helps these systems talk to each other, optimizing energy production across an entire field. But let's go beyond generation, because photonics is also transforming how energy is used. Inside factories and data centers, ultra-fast lasers now perform what's called cold ablation, removing or shaping materials without generating heat. This reduces waste, improves precision, and saves massive amounts of energy. In micro and nanoscale manufacturing, two-photon polymerization enables 3D printing of intricate structures, everything from biomedical implants to aerospace optics, built one photon at a time. It's manufacturing with light, not metal. Even the digital world is becoming more photonic. Inside massive data centers, fiber optic links are replacing traditional copper wires. Light-based computing reduces both latency and heat, cutting cooling requirements and emissions by huge margins. And in our cities, photonic sensors are quietly building the foundation for smart infrastructure. Fiber Bragg gratings embedded in bridges, pipelines, and tunnels can detect stress or cracks in real time,
a kind of optical nervous system watching over our built environment. These systems feed data into digital twins, virtual replicas of physical infrastructure, helping cities predict failures before they happen. But perhaps the most awe-inspiring impact of photonics lies far above us, in orbit. From satellites equipped with hyperspectral imagers to LiDAR-based climate monitoring, photonics gives us eyes on the Earth itself. Carbon dioxide, methane, aerosols, each leaves a distinct optical fingerprint in light. By comparing the absorption and reflection of different wavelengths, scientists can map pollution, monitor deforestation, or even track methane leaks in real time from space. Fluorescence LiDAR can detect the faint glow of chlorophyll, revealing the health of crops and forests. Bathymic LiDAR penetrates coastal waters to map coral reefs and monitor erosion. These light-based tools let us see environmental change before it becomes irreversible. Of course, building all this technology is no small task. Photonics requires exquisite precision. Manufacturing photonic chips, where light travels through microscopic waveguides, demands atomic-scale alignment. Sensors must survive heat, radiation, and harsh outdoor environments for decades. And even as we make devices to protect the planet, we must ensure that the photonics industry itself is sustainable, minimizing rare materials and energy-intensive processes. But the frontier keeps expanding. Neuromorphic photonics are now emerging, using light to perform brain-like computation at speeds and efficiencies impossible with electrons. This can enable real-time AI-driven climate modeling, global-scale predictions processed at the speed of light. And lab-on-chip photonic sensors are shrinking entire environmental laboratories to the size of a credit card, enabling precision monitoring in the field, on drones, or even by citizen scientists. And photonic materials designed for radiative cooling, surfaces that reflect sunlight while emitting infrared heat, could passively cool buildings without electricity, reducing urban heat islands and energy demand. Photonics connects the microscopic to the planetary, from a single photon trapped in a nanocavity to a laser pulse measuring Earth's atmosphere. It's the thread of light weaving through every layer of our sustainable future. So as we search for answers in the climate fight, maybe it's time to look not just to the ground or the wind or the ocean, but to the light itself. Because in the end, it may be photons, the smallest, fastest messengers in the universe, that help us build a brighter, cooler, and more resilient world.
Thanks for watching. Subscribe, follow, or visit idsth.com for more cutting-edge defense and tech insights. See you in the next one.